Alright, so here's a worked example of a one-way ANOVA, and we're going to do a really simple example where we have three groups, and these are the scores. Each group has three people in it, and these are the scores for each person in each group, and their averages. So group 1 has a mean of 2, group 2 has a mean of 4, group 3 has a mean of 6, and if you add up all 9 scores and divide by 9, you'll find that the grand mean, or x bar total, is 4. So the grand mean is 4, and each of the group means are there, 2, 4, and 6. Then the next step in doing the ANOVA is to calculate the sum of squares error, also known as the sum of squares within. So you can see it's got an E or a W. You can use either one. And the formula is right here. You just find the sum of the deviations between each individual score and their own group mean squared. So over here in group 1, you see you take the first score minus its group mean, square it, and you get 1. And you do that for each score in the group, and you get the sum of the square deviations for that group is 2. The sum of the square deviations for group 2 is also 2, and the sum of the square deviations for group 3 is also 2. And then when you add those up, summing the square deviations, you get 2 plus 2 plus 2 equals 6. So that's the sum of the squares error, SSE. Then you need to find the sum of the squares between groups, SSB, and to do that you take the sum of the square deviations between each group mean and the grand mean, and then multiply that by the number of cases in the group. So here, for the first group, there's 3 people in the group. This right here is the group mean for group 1. That's the grand mean. Square that difference. 2 minus 4 squared. 2 minus 4 is negative 2. You square that, you get 4. 4 times the number of cases in the group, which was 3. 3 times 4 is 12. For group 2, you see that the difference between the group mean and the grand mean is 0. So 3 times 0 is 0. And for group 3, the group mean is 6. The grand mean is 4. Square that, and you end up with 4. 4 times the number of cases in the group, which is 3. 3 times 4 is 12. And then you just take the sum of these squared deviations, and you get this value. 24 is the SSB. Sum of the square deviations between groups. Then you need to find the degrees of freedom for each for the degrees of freedom error and the degrees of freedom between groups. Degrees of freedom error is here. Number of cases, total, which is 9. Number of groups, which is 3. 9 minus 3 is 6. So the degrees of freedom error is 6. Degrees of freedom between groups. Number of groups, 3 minus 1. The DFB, the degrees of freedom between groups, is always the number of groups minus 1. And in this case, that gives you 2. So the DFB is 2. The DFE is 6. And you use these degrees of freedom to convert the SSE into the MSE. So if you look here, this formula right here, sum of squares error divided by the degrees of freedom error, the SSE was 6, and the degrees of freedom error was 6, and 6 divided by 6 is 1. The MSB is going to be the sum of squares between groups divided by the degrees of freedom between groups. So that's this right here. Sum of squares between groups was 24. Degrees of freedom between groups was 2. And 24 divided by 2 is 12. So once you have your MSB and your MSE, remember this MSE is basically the average difference between the group means, and this MSE is basically the standard error. Both of these are squared though. And this is what goes into the formula for the F value in the ANOVA. Remember our MSB was 12, our MSE was 1. 12 divided by 1 is 12. That's our F value. And then we look at Appendix C to find our critical F value. This is our F critical. And that's with 2 degrees of freedom between groups, 6 degrees of freedom error. And when you look in Appendix B, you'll find the critical value is 5.99. This is with an alpha level of 0.05. And we can see that our observed F value of 12 is larger than our critical value, so our results are statistically significant. Now, when we find a statistically significant F value, here's what we know. We know that there's differences between the population means, but we don't know which specific population means are different from each other. So it could be, if you got 3 groups that you're comparing, it could be that 2 of the groups have significantly different means, but the other 2 don't. So you got to take it one step further to figure out which group means are actually significantly different from each other. And to do that, we do a Tukey test. A Tukey test is basically like a t-test, but it takes into account how many groups are being compared. So you got to find a standard error for the denominator of the Tukey test, and that is the MSE, the mean square error, which we calculated before, divided by N1. And what that N1 means is the number of cases in a single group. So each of our groups had 3, so the N in this standard error formula is going to be 3. The MSE, the mean square error that we calculated before, was 1, and the square root of 1/3 is 0.57, and that goes into the denominator of our Tukey tests. Now, this right here is how you kind of do the symbol. So that big T means Tukey test, and 3 minus 1 means group 3 compared to group 1. Group 3 had a mean of 6. Group 1 had a mean of 2. So what you end up with is 6 minus 2 is 4, divided by the standard error, and the value you get is 7.01. And that is the observed Tukey value to compare group 3 to group 1. We do the same thing over here to compare group 2 to group 1, and we only need to do this one once because the difference between group 2 and group 1 is the same as the difference between group 3 and group 2. So it's going to produce the same observed Tukey value. And when we do the calculations, we find the observed Tukey value is 3.51 for both of those comparisons. Now, we look at Appendix D, and in Appendix D, the top of Appendix D does not have degrees of freedom between groups. It has the number of groups being compared. So we're comparing 3 groups, and we use our degrees of freedom error for the left-hand column, which in this case was 6. So 3 groups being compared, 6 degrees of freedom error. We find the critical T value, the critical Tukey value, right here, of 4.34, and that is for an alpha level of 0.05. So for our first comparison, comparing group 3 to group 1, we got an observed value of 7.01, critical value of 4.34. That is a significant difference, statistically significant. And for these two comparisons here, group 2 to group 1 and group 3 to group 2, we can see that our observed t-value is less than our critical t-value, so that is not statistically significant. And then we can wrap words around our results. So group 3, on average, that population mean is higher than the population mean for group 1. There's no difference on average between the population means of group 2 and group 1, or between the population means of group 3 and group 2. And if we were to be doing this for real, we would name the groups, and we would name the variable that we're talking about. So say group 1 is California, group 2 is Alabama, and group 3 is Mississippi. So we find, on average, in the population, Mississippi has more neckties than Californians, something like that. But there's no difference between California and Alabama in the number of neckties owned on average in the populations, and there's no difference between whatever the other thing, Mississippi and Alabama, something like that. Anyway, you get the idea, I hope. Hope that helps.